Welcome to FMSP Online Revision. This session is for OCR FP1 Matrices. So let's start by having a look at the specification for matrices, and then what we'll do is we'll work through some exam questions to try and help you get as many marks as possible when it comes to the exams. So the specifications first of all. So the first three we've got here. So we've got to be able to do things like add, subtract and multiply matrices, recognise the null or the zero matrix, so that's a matrix in which all entries are zeros, and then the identity or unit matrix for 2 by 2 or 3 by 3. So for example, for a 2 by 2 matrix we use the letter I and the matrix would be 1 0 0 1. We've then got to be able to recall the meaning of terms like singular and non-singular as applied to square matrices, and for 2 by 2 and 3 by 3 matrices we've got to be able to evaluate determinants and find inverses of non-singular matrices. So just again remember that if we have a matrix M, then we calculate the determinant. Then if the determinant is equal to 0, then we say that it is a singular matrix. And in that case, the inverse does not exist. So in order for an inverse to exist, the determinant cannot be equal to 0. And then in part C, we've got to understand and use the result that for non-singular matrices, that the inverse of AB is equal to the product of the inverse of B and the inverse of A. And this result is used in quite a lot of questions, so you should actually learn that result. The next part in the specifications, we've got to understand about using 2 by 2 matrices to represent certain geometrical transformations. So in particular here there are some points. We should recognise the product AB. It represents the transformation B followed by the transformation A. So again, remember that the order in which we multiply matrices is all very important, and it does matter. So AB represents B followed by A. We should know that the determinant of the matrix gives the area scale factor. And then in part 3, we should be able to find matrices associated with transformations, in particular rotation, reflection, enlargement, stretch and shear, and those will be required. And it's worth remembering that if we have a transformation matrix M, let's say that matrix is A, B, C, D, then the image of the point 1 0 will be given by the first column of that matrix, A, C, and the image of 0 1 will be given by the second column, B, D. And if we actually use this, it should help us to be able to write down the matrix associated with the transformation if we can find the image of each of these two vectors. And not only that, given a matrix, we should be able to work out what the image is. So it works both ways. There are some matrices given in your formula book. So for example, the rotation of theta about O, that matrix will be given to you. And there is another one which is the reflection in the line y equals tan theta x. So again, it's worth just checking your formula books for those. And some more points in the specification. We should be able to formulate a problem involving simultaneous equations in 2 or 3 unknowns. And you should recognise that as a problem involving the solution of a matrix equation. And understand that there may be cases concerning the consistency or inconsistency of 2 or 3 linear simultaneous equations. Relate them to the singularity, that is when the determinant is equal to 0, of the corresponding matrix and solve consistent equations. So we will be looking at a lot of these points as we work through some questions. So let's make a start. So the first question, it is number 1, so it's a short question from the beginning of the paper. We're given a matrix A and we're asked to find A minus 4i. And then in part 2, given that A is singular, then we've got to find the value of little a. So part 1 first of all. So just a matter of substituting in carefully. So A is the matrix A, 2, 3, 4. And from that we've got to subtract 4 times the identity matrix. So just checking that carefully. So remember, subtracting means we're going to just subtract corresponding terms. So it's going to be A minus 4, and then 2 minus nothing, 3 minus nothing, and then it's going to be 4 minus 4, which is nothing. And then in part 2, it says, given that A is singular. So remember that if A is singular, then that means that the determinant of A is equal to 0. So we need now to be able to find the determinant. So the determinant of A is going to be A times 4, that's the product of the elements in the diagonal from top left to bottom right, minus the product of the elements in the other diagonal. So it's going to be 4a minus 6. And if that is equal to 0, then that means that 4a is going to be equal to 6 and a is going to be equal to 3 over 2. So 5 marks for the question in total. There was 1 mark here for getting 2 elements correct and another mark for getting the remaining 2 elements correct. And then in the second part you got a mark for putting the determinant of a equal to 0, a mark for evaluating the determinant of a, 4a minus 6, and then an accuracy mark for working out the value of a, which was 3 over 2. So another question, this time on transformations. So we have a matrix X given to us, and part 1 we've got a diagram in the printed answer book, and it shows the unit square OABC. The image of the unit square under the transformation X is given by OA-B-C-, and we're asked to draw and label OA-B-C'. And then in the second part, the transformation represented by X is equivalent to a transformation A followed by a transformation B. And we're asked to give a geometrical description of each of these transformations and state the matrices that represent them. So, the first part. So we have a matrix, as I say, 0, 3, 3, 0, and we want to find the image of the unit square. So we'll write down, this is our transformation matrix. Now the unit square is the origin, the point 1, 0, the point 1, 1, and the point 0, 1. And those are shown on our diagram. So this is O, this is A, this is B, and this is C. And what we have to do is to find the image of each of those points. Now you could do it as 4 little separate multiplications, but I've just chosen to do it as a 2 by 4 matrix over here. So we'll multiply each of these in turn. So the origin remains fixed, so that's going to be 0, 0. Then we have 0 times 1 plus 3 times nothing, which is nothing. 3 times 1 plus 0 times 3, which is 3. So that now is giving us the image of A, which is A dash. We'll do the same thing for B, so it's 0 times 1 plus 3 times 1, which is 3, and 3 times 1 plus 0 times 1, which is 3. So we now have the image of B, which we'll label B dash, and then we do C. 0 times 0 plus 3 times 1 is 3, and 3 times 0 plus 0 times 1 is nothing. And we now have the image of C dash. So if we mark these on the diagram, then the image of A is 0, 3, so that's going to be up here, and we'll label that A dash. And the image of B is 3, 3, so we'll put that up here, and we'll label that B dash, and the image of C is 3, 0, so we'll label that C dash. And it says draw and label OA dash, so I'll draw our image. So we're going to get 1 mark for A dash, 1 mark for C dash, and then 1 mark for the correct square. So if we move on to part 2, so the transformation x is equivalent to A followed by B. So when we're doing this question, that means we'll write down x is equal to BA. And looking at the matrix, if you remember, we were told that the matrix X was 0, 3, 3, 0. And we saw what happened. We saw that there was some sort of an enlargement taking place, and hopefully we also saw, if we just look back at the last slide, that A dash started, well, A was on the x-axis and A dash was on the y-axis, and C started on the y-axis and ended up on the x-axis. So hopefully you will see that there was a reflection involved, and in fact it was a reflection in the line y equals x. So when we reflect in the line y equals x, 1, 0, remember, is mapped onto 0, 1, and 0, 1 is mapped on to 1, 0. So the image of that, the matrix for that, is going to be 0, 1, 1, 0. So that matrix is going to be the first one that we did, so we'll call that A. And then you'll also remember that our square was enlarged by a factor of 3. So there was an enlargement, scale factor 3, and if you can't write down the matrix immediately, then just remember that 1, 0 was mapped onto 3, 0, and 0, 1 would be mapped on an enlargement to 0, 3, and so the matrix, which in this case we'll call B, will be 3, 0, 0, 3. And you can check that those two matrices would in fact multiply together to give x. In terms of marks, 4 marks for the question. You got 1 mark for the reflection in the line y equals x. You might even have got a mark if you'd written y equals minus x, but to get the second mark you would need to know that it was the line y equals x and that this was our matrix. So you needed the correct matrix. And similarly for the enlargement, as long as you wrote down the fact that it was an enlargement scale factor plus or minus 3, you would get a mark, but you would get the second mark for knowing that it was actually scale factor plus 3 and that this was our matrix. So we'll now look at a question involving 3 by 3 matrices. So this is a question 9, so it's a longer question worth 9 marks. So if we just read through the question first of all, and then what we'll do is we'll break it down into bits. So the matrix M is given by, and you've got this 3 by 3 matrix which has got a letter A in it. First of all, we've got to find, in terms of A, the determinant of M. Hence, so once we've found the determinant of M, we've got to find the values of A for which the inverse m to the minus 1 does not exist. And then in part 3, we've got to determine whether the simultaneous equations that are given here, where k is a non-zero constant, so you've got a constant k here, you've got to determine whether they have a unique solution, no solution, or an infinite number of solutions, and we've got to justify our answers. So let's take the first two parts, and we'll have a look at those first of all. So we've got to find the determinant of M. So remember that when you're finding the determinant, you can in fact expand by any row or any columns. And if there are lots of zeros in a row, 1 or 2, or a column, then it's a good idea to use that row or column. But in this case, there aren't any zeros, so I'm just going to expand by the first row. And so when we do this, to find the determinant, associated with a 3 by 3 matrix is a matrix of signs. So we need to use this when we're finding either the determinant or in fact the inverse of a matrix, a 3 by 3 matrix. So when we expand by the first row, then the first term is going to be positive, the second term is going to be negative, and the third term is going to be positive. So we're going to have the first term positive, and the first term we get, so we're imagining that we're going to, so the entry is an A, we're going to cross out the first row and the first column, and then we're finding the determinant of this 2 by 2 matrix which is left. So it's going to be A upon A minus 2. Now the next term is going to be a negative, and then the entry itself is negative A. We're again imagining that we're going to cross out the first row and that middle column, and we're finding this determinant of the matrix 3, 1, 4, 1, which will be 3 minus 4. And then the third term is positive, the entry is 1, and the matrix is this one here, and that has determinant 6 minus 4a. So we now need to just simplify all of that. So we're going to get a squared minus 2a. That is going to be a plus, and then 3 minus 4 is minus 1, so it's going to be minus 1a, and then we'll have a 6 minus 4a. And if we simplify that, we end up with 8a squared minus 7a plus 6. So we have found, in terms of a, the determinant of m. And we're then in part 2 asked to find the values of a for which the inverse does not exist. So remember, if determinant of m is equal to 0, then the inverse of m does not exist. So that's the theory behind it. And of course we therefore want to find the values of a for which a squared minus 7a plus 6 are equal to 0. And that implies, and it does factorise, a minus 6 upon a minus 1 is equal to 0. So we have two values, a equals 6 or a equals 1. So if we just have a look at the marks for those two parts first of all, then in part 1 you're going to get a method mark for attempting your expansion of either a row or a column of the matrix. You're going to get a method mark also for getting an evaluation of a 2 by 2 determinant. These bits in brackets were evaluations of 2 by 2 determinants, and then you're getting an accuracy mark if you end up with the correct expression. And then in part 2 you're getting a method mark for mentioning the fact that the determinant is equal to 0 is the condition for the inverse not to exist, and then you're getting two accuracy marks, one for each of the values of a. So we'll have a look now at part 3. So in part 3 we're now asked to determine whether these set of equations, simultaneous equations, have a unique solution, no solution, or an infinite set of solution. So in part 1, just up here, I have reminded you just of the matrix that we were given at the beginning. We found that the inverse did not exist for these two values, for a equals 1 or a equals 6. So if you have a look at these equations, then you should be able to see that these are the equations which can be represented by this transformation matrix where a is equal to 6. So that was the first thing that you needed to see. So a equals 6. So that means the determinant of m is equal to 0. And we of course found that in part 2. And so that implies that there is no unique solution because the inverse does not exist. What we then have to determine now is whether there is no solution at all or whether there is an infinite set of solutions. So we'll do that. We can't use matrices because we can't find the inverse, so we're going to take these equations and we'll solve them simultaneously. So let's just call the equations 1, 2 and 3. So I'm going to take the first two equations, 6x minus 6y plus z equals 3k, and the second equation, which is 3x plus 6y plus z equals 0, and I'm going to add them. So hopefully you can see that by adding these equations then I'm going to eliminate y. So if I add 1 and 2, then I end up with 9x plus 2z is equal to 3k. So we have now eliminated y from the first two equations, so we now need to eliminate y from another pair of equations. So I'm going to take the third equation and I'm going to multiply it by 3. So I'm going to take the third equation and multiply it by 3. So I end up with 12x plus 6y plus 3z is equal to 3k, and I'm going to call that equation equation 4. So I've just taken this third equation and multiplied it by 3. But the advantage of doing that is now I could add the first equation and the fourth equation, and I'll get 6x plus 12x, which is 18x. The y terms will again disappear. We've eliminated them, and then we'll get z plus 3z, which is 4z. And that will be equal to 3k plus 3k, which is equal to 6k. Now hopefully you can see that that equation, 18x plus 4z equals 6k, is exactly twice this equation. So it's twice the equation 9x plus 2z equals 3k. So that means that the equations are consistent. And when the equations are consistent, it means that we are going to have an infinite set of solutions. If this had not worked out here, if we'd ended up with a 7 or an 8k here, for example, then we might have had inconsistent equations, in which case there'd be no solution at all. So 3 marks for that last bit. So you got 1 mark for attempting to eliminate a variable, so we eliminated y from the first two. You'd then get a 2nd mark for doing it with another pair and getting the second equation in x and z, and then you get 1 mark for justifying the fact that there is an infinite set of solutions. So I'm going to finish the session here and just remind you that it is really important now that you do as many questions as possible. So work through as many exam papers as you can, because that's always the best way for you to revise.